Albert Einstein's theory of relativity is one of the most revolutionary and influential scientific theories of the 20th century. It consists of two main components: special relativity and general relativity. Here's an overview of both theories. 1. Special Theory of Relativity, 1905. Principle of relativity. Einstein's special theory of relativity is built on the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion. This means that there is no absolute reference frame. Motion is relative. Invariance of the speed of light. One of the most famous consequences of special relativity is that the speed of light in a vacuum, denoted as c, is constant and the same for all observers, regardless of their relative motion. This is a fundamental postulate of the theory. Time dilation. Special relativity introduces the concept of time dilation, which means that time passes differently for observers in relative motion. Specifically, time appears to slow down for an observer in motion relative to a stationary observer. This effect becomes significant as an object's speed approaches the speed of light. Length contraction. Special relativity also predicts length contraction, meaning that objects in motion appear shorter in the direction of motion when measured by a stationary observer. Mass-energy equivalence. Einstein's famous equation, E equals mc squared, demonstrates the equivalence of mass and energy. It states that the energy, E, of an object is equal to its mass, m, times the speed of light, c, squared. This equation has profound implications, including the idea that mass can be converted into energy, as in nuclear reactions. 2. General Theory of Relativity, 1915. Principle of equivalence. The general theory of relativity extends the principles of special relativity to include gravity. Einstein proposed that there is no distinction between gravitational forces and acceleration. In other words, objects fall in a gravitational field because they are following curved paths through spacetime, not because they experience a force. Curvature of spacetime. General relativity introduces the concept that massive objects, like planets and stars, warp or curve the fabric of spacetime around them. This curvature causes objects to move on curved trajectories in the presence of gravity. Gravitational redshift. General relativity predicts that light traveling out of a gravitational field will be redshifted, or shifted toward the red end of the electromagnetic spectrum. This effect has been experimentally confirmed. Prediction of the perihelion of Mercury. One of the earliest experimental confirmations of general relativity was its ability to explain the anomalous precession, slow rotation, of Mercury's orbit. Einstein's theories of relativity have been confirmed through a variety of experimental tests and have become fundamental principles of modern physics. They have profound implications for our understanding of space, time, gravity, and the behavior of objects at high speeds. They also play a crucial role in various fields, including astrophysics, cosmology, and the development of technologies like the Global Positioning System, GPS.